In the previous lecture, we have started to deal with the Bragg-Williams approximation, or you can say the Ising model in Zeroth approximation. Actually, the basic problem which we are going to see is to deal with the problem of ferromagnetic phase transition. You know that a ferromagnetic phase transition is actually a second order phase transition and applying the Ising model and considering the facts of Bragg-Williams approximation, we can deal this problem very easily. Okay. So in the first part of the lecture on this subject, you have seen the calculation of the interaction energy when a ferromagnetic substance is placed in an external magnetic field. The substance gets magnetized, and there are two types of interaction you have seen. First one was intrinsic interaction, which is also called a spin-spin interaction, and the second one was the external or extrinsic interaction, that is the interaction of the magnetic dipoles of the system with the external magnetic field. And due to these two interactions, interaction energy is developed in our system, and we have calculated the value of the interaction energy in the first part of this lecture. So I have mentioned here for your convenience the final result which we have obtained in the previous lecture for the interaction energy, and this is given like EI equal to minus half gamma epsilon nm square minus mu h mn. Actually, you know that in this expression, m is the long range order parameter and its value lies between -1 and +1. And apart from this, the quantities used in this expression are already known to you because you have studied this fact in your previous lecture. You know that this gamma is the coordination number or the nearest neighbor number, and epsilon is the interaction energy, or you can say this is the coupling constant when we consider that the interaction is isotropic. Okay, and n represents the total number of spins, that is the sum of the up spin and down spin. Okay. Now in this lecture, this is actually the concluding or final lecture on this Bragg-Williams approximation to deal with the problem of phase transition of ferromagnetic substance. So in this lecture, actually we will find the energy of the system, which is also called free energy of the system or Helmholtz free energy. And then applying the condition of equilibrium of the system, we can achieve our goal. And for finding the Helmholtz free energy, you know from the definition of Helmholtz free energy, which is defined like that E minus Ts, where S actually is the entropy. So in a step-by-step calculation, we will first of all calculate the entropy of the system, and after the calculation of entropy, you will be able to find the Helmholtz free energy, and then we will apply the condition of equilibrium of the system. So I have mentioned here that first of all we are going to find the entropy of this very system. Okay. You know, in statistical mechanics, there is a well-known theorem regarding this entropy proposed by Boltzmann, and we will apply or we will use this famous Boltzmann entropy theorem to find the entropy of this system. Okay, and it is well known to you that according to this theorem, the entropy of the system S is given by K ln W. Okay, where you know that this K is the Boltzmann constant and W is the maximum thermodynamical probability of the system. When you say this maximum thermodynamical probability, what will be its value? It depends on the system. So in the present context, you know that there are total number of spins n, and when you talk about the maximum thermodynamical probability, it means you have to know what will be the probability of up spin. Okay. So this calculation of W becomes simple. You have only to use the concept of permutation and combination, and the W will represent simply the number of ways in which you can pick up n plus things out of n things. Okay. So according to the theory of permutation and combination, you know that the number of ways by which n plus things can be chosen from n things, that is given by W equal to nc n plus. Okay, and you know that this nc n plus is simply equal to n factorial divided by n plus factorial times n minus n plus factorial. Okay, but you know that this n plus, which represents the number of up spin, plus n minus, which represents the down spin, the sum of these two is equal to n. So this n minus n plus will be simply equal to n minus. So instead of this n minus n plus, I have written here n minus. So finally you get W is equal to n factorial divided by n plus factorial times n minus factorial. Okay. Now, as in the expression of entropy, you have seen that S is equal to K ln W. So first of all, we will find the value of log W. So let us take the natural log of this expression. Okay. And when you will take the natural log of this expression, what will be the result? The result will be ln n factorial minus ln n plus factorial minus ln n minus factorial. Okay. Now you know all these factorial terms can be simplified by using the famous Stirling formula or Stirling approximation. And you have used this Stirling approximation several times in the course of your statistical mechanics. So you are well known to it. So using this Stirling approximation, you can write ln W equal to what? For ln n factorial, according to Stirling approximation, we will write n ln n minus n. Okay. And for ln n plus factorial, we will write n plus times ln n plus minus n plus. And similarly for ln n minus factorial, you will write this n minus ln factorial, n minus ln n minus minus n minus. Okay. Now, we will simplify this result to some extent. So ln n minus n has been written at ease, and now when you will remove this bracket, the sign will be just changed, and this will be n plus ln plus, and here n minus ln minus, okay, with minus sign, and this n plus and n minus will become plus due to this minus sign outside of the bracket. And so I have written it here plus n minus. But you know that this n plus n minus is n, so this last term will cancel by this minus n. And so we will get ln W equal to n ln n minus n plus ln n plus minus n minus ln n minus. Okay. So I have written it here, you can see. Okay. Now you know that this n is equal to n plus n minus, and this log n can be written as log 1 by n minus log 1 by n. So I have taken here minus sign, and instead of this log ln, we have written ln 1 by n. Actually, our final aim is to express this logarithmic value of w in terms of the long range parameter m. And for doing that, there will be some algebra. So we are going to follow those algebra by which we will be able to express the expression for ln w in terms of m. And for that we are doing these things. Okay. And the remaining two terms you can see are at each. Okay. Now, let us multiply this log ln 1 over n by this factor inside the bracket. So this will be n minus n plus log 1 by n, and then there will be plus n plus log n plus. Okay, n plus log n plus. Actually, n plus log n, sorry, this will be not plus but minus. I have mistaken here. You can see this is in fact minus. Sorry, minus has been taken in fact as a common factor. So here will be plus. Okay, this will be plus because we have taken this minus as a common factor, and all the terms in this expression is negative. So when you will take minus as a common factor, all terms will be positive. Okay, inside the bracket. So here there is plus sign. Okay, and this n minus times log 1 by n, I have written it here, and the remaining term this n minus log n minus has been written here. Okay, now you know that log a plus log b is log a into b. So you can take this n plus as a common factor, and the remaining terms will be log 1 by n plus log n plus, and that will be written as log n plus by n. Okay, and similarly the sum of these last two terms will be written as n minus log n minus by n. Now to express this expression in terms of the long range parameter small m, we do a simple algebra. You have to multiply by the factor n both in numerator and denominator. So I have written here n, and also in denominator I have written n here and here. So your result is minus n plus over n log n plus by n plus n minus by n log n minus by n. Okay. Now I have mentioned only one result of the previous lecture, but you have studied so many results in the previous lecture, although I have not mentioned it here all. So you can remember the first part of the lecture, and you can see that we have obtained in the previous lecture that this n plus by n is equal to what? You can see the first part of the lecture. This is equal to 1 over 2 times 1 plus m. Okay, so instead of n plus divided by n here and also here, I have written 1 by 2 1 plus m. Okay, and similarly you have also seen in the previous lecture that n minus divided by n, that is equal to 1 by 2 times 1 minus m. So the second term has been written like this. Okay, now see the first term, 1 over 2 times 1 plus m, it is at each. Okay, minus n is at each. Okay, and log half times 1 plus m, log a times b is equal to log a plus log b. So you can write this log 1 by 2 plus log 1 plus m. And similarly in the second term you can write 1 by 2 times 1 minus m, and log 1 by 2 plus log 1 minus m. Okay. Now we will multiply by the factor 1 by 2 log 1 by 2 times 1 plus m to the two terms inside this curly bracket, and also in the second term we will do the same thing. Okay. Now let us see. This equation will be then written as log w equal to minus n times 1 by 2 times 1 plus m log 1 plus m plus 1 by 2 times 1 plus m log 1 minus m, and minus 1 by 2 1 plus m log 2. Although in our expression there was log 1 by 2, so log 1 by 2, you know, this is equal to minus log 2. So here I have used minus sign, and log 1 by 2 has been replaced by minus log 2. Similarly, here you can write minus 1 by 2 times 1 by 1 minus m log 2. Okay. Now see the last two terms. When you will multiply this, you will get minus half log 2, okay, and minus 1 by 2 m log 2, okay. And when you will multiply it here, you can see this will be minus 1 by 2 log 2, minus 1 by 2 log 2, and minus minus will be plus, and there will be, sorry, this will be plus 1 by 2 m log 2, log 2. So this and this will cancel out, and only the terms in the last term we will have minus 1 by 2 log 2 or minus 1 by 2 log 2. So this will be 2 times of minus 1 by 2 log 2. 2 will cancel out, and so the sum of the last two terms will be simply minus log 2. So you can see I have written here minus log 2. Also here you can see. So this result is what? This is minus n times 1 by 2 times 1 plus m times log 1 plus m plus 1 by 2 times 1 plus m times log 1 minus m minus log 2. Okay. So in this way we have obtained the value of log w in terms of the long range parameter m. This long range parameter m is the parameter in terms of which we will discuss the final problem. Okay. So now you can find the value of entropy of the system, because you know S is equal to K log W. So simply multiply this above result by the Boltzmann constant K and you will get S. So S is equal to what? This is minus Nk times 1 over 2 times 1 plus m times log 1 plus m plus 1 by 2 times 1 plus m times log 1 minus m minus log 2. Okay. So in this way we have calculated the value of entropy. But our final aim is what? Our final aim is to find the Helmholtz free energy. So now apply the definition of this Helmholtz free energy. You know, Helmholtz free energy is in general denoted by the symbol F, and it is a thermodynamical potential, and it is defined by E minus Ts. E is actually the internal energy, and here in this present problem actually this E is equal to what? Actually here this E is equivalent to EI, which we have already obtained in the previous lecture, and I have mentioned its value earlier in this lecture. This is the value of EI. So let us substitute the value of EI in this expression. This is the value of EI, okay, and minus Ts, you know, S is defined in this equation 3. So we will simply multiply this equation 3 by t. So this will be, since this is minus, but already there is minus sign here, so this will become plus. So this is nkt times minus log 2. I have written this minus log 2 first, and plus 1 by 2 times 1 plus m times log 1 plus m plus 1 by 2 times 1 minus m times log 1 minus m. So this is the expression for the Helmholtz free energy. Now you know that if the system will be in equilibrium, definitely this energy should be minimum. And as it is evident from this expression in equation 4 for the Helmholtz free energy, that this Helmholtz free energy is the function of a small m, which is long range parameter. Okay, apart from the temperature, apart from this gamma, apart from epsilon. So when we will minimize this f with respect to m, then you can use the condition for minima, that if the system will be in equilibrium, then we can write del f by del m equal to 0. I have not written df by dm because we have not taken ordinary derivative, since f is not only a function of m, but it is also a function of temperature, it is also a function of gamma and epsilon. But our aim is to minimize this Helmholtz free energy with respect to this long range parameter. So I have considered this condition for minima as del f by del m equal to 0. Now let us substitute the value of f here. This is del m, and inside this square bracket I have written the expression for f, which you have just seen. Okay. Now we will simply differentiate the function inside this square bracket. You can see in the first term the derivative of m square will be 2m, and this 2 and that 2 will cancel out. So the first term will be minus gamma n epsilon m. Okay. In the second term there is m, so del m by del m will be 1. So the second term remains minus mu hn. Okay. Then nkt, and log 2 is a constant term, so its derivative is 0, so it is removed from here. And now we will differentiate with respect to m the last two terms. In last two terms you can see there is a product of two functions. So following the rules of differentiation of product of two functions, you will get what? When we will take this 1 by 2 times log 1 plus m at each, and we will differentiate this 1 plus m. The derivative of 1 plus m with respect to m will be 1. So the first term is 1 by 2 log 1 plus m. Okay. Now we will differentiate this log 1 plus m. Okay. Log 1 plus m we will differentiate. You know that log 1 plus m, when differentiated with respect to m, this will be 1 by 1 plus m times 1. Okay. So this 1 by m and the multiplicative factor 1 plus m will cancel out, and your result will be simply 1 by 2. Okay. And the similar manner you can differentiate the last term, and then you will get this is minus half log 1 minus m minus half. Okay. Now this plus half and this minus half will cancel out, and you can see that if we will bring these first two terms in LHS, this will become plus, and this is gamma epsilon m plus mu h. And in RHS there will be what? There will be, in fact, n is a common factor. It is present in all terms, so n has been removed. And so in RHS there will be kt divided by 2 and log 1 plus m minus log 1 minus m. This will be log 1 plus m divided by 1 minus m. Okay, and so from here you can easily write log 1 plus m by 1 minus m. This is 2 times of gamma epsilon m plus mu h divided by kt. Now let us consider gamma epsilon m plus mu h divided by kt equal to x. So this can be written as 2x. We have supposed it. Okay, x is equal to gamma epsilon m plus mu h divided by kt. Okay. Now we can see from here that 1 plus m divided by 1 minus m, this will be equal to e to the power 2x. And this e to the power 2x, you can write e to the power 2x divided by 1. Okay. Now using the rules of componendo and dividendo, you can write 1 plus m minus 1 minus m divided by 1 plus m plus 1 minus m. Because you know from componendo and dividendo that if a by b is equal to c by d, then we may write a minus b divided by a plus b equal to c minus d divided by c plus d. Using this rule of componendo and dividendo, you can write like this. Okay. Now you can see this in the numerator. 1 will cancel out and the remaining factor will be 2m. Okay, in LHS. And in denominator, m will cancel out and remaining term will be 2. So this 2 and 2 will cancel out and LHS becomes m. Okay. And so m is equal to e to the power 2x minus 1 divided by e to the power 2x plus 1. And you know from trigonometry that this is equal to simply tan hyperbolic x. Okay. And this is actually the well-known result of the Weiss theory of ferromagnetism. Okay. Actually in lower classes we study Weiss theory of ferromagnetism, and this is the well-known result of that theory. Okay. Now after getting the value of this m, which also represents the magnetic moment per lattice set or per atom, you can say. So after getting this value, you can define what will be the total magnetization of this ferromagnetic specimen. Actually this result which I have written here have been already derived in the first part of the lecture. Okay, so I have mentioned it here directly that this magnetization m is equal to mu times nm. Okay, but in equation 6 we have obtained the value of m, so let us substitute the value of m here and your result will be mu n times tan hyperbolic x. But this x you can see is equal to what? X is gamma epsilon m plus mu h divided by kt. So instead of this x, I have written here this. So m you get mu n tan hyperbolic gamma epsilon m plus mu h divided by kt. Okay. This is the value of magnetization. Okay. Now you know that when magnetic field is removed, then in case of paramagnetic substance, the magnetic moment instantaneously vanishes. Okay. After removing the magnetic field, there is no magnetism in paramagnetic substance. But in case of ferromagnetic material, even after the removal of the external magnetic field which magnetize actually the substance, magnetic moment does not vanish. It does not become zero. So, in fact, in absence of external magnetic field, or you can say magnetizing field, the remaining or the residual magnetic moment is called the spontaneous magnetization. So to get the value of spontaneous magnetization, what you will do? We will simply put H equal to 0, because H is the external magnetizing field. So when you will make H equal to 0, then the remaining magnetization is called a spontaneous magnetization, and it is denoted by the symbol Ms. So for getting the value of Ms, that is the spontaneous magnetization, we will simply put H equal to 0. So after putting H equal to 0, what will be your result? Your result will be M equal to mu n tan hyperbolic gamma epsilon m by kt. But now this m is denoted by ms, and this small m will be also denoted by ms. Okay. So I have written here, you can see that ms equal to mu n tan hyperbolic gamma epsilon ms by kt. Okay. Now again you know that this m is equal to mu times nm. So you can write m equal to m divided by mu n. And so if you want to find the spontaneous value of this order parameter, this can be written as ms equal to ms divided by mu n. Okay. And therefore, instead of this ms in this result, which I am just marking here, you can substitute ms divided by mu n. So this result which I have written here now can be written as ms equal to mu n tan hyperbolic gamma epsilon capital Ms divided by mu n kt. Okay. I have used this result. Okay. Now, as you can see from this equation 7, that ms are divided by this mu n, ms divided by mu n, this will be tan hyperbolic gamma ms divided by kt. In fact, from here, not from equation 7, but from this equation, you can write this expression. ms divided by mu n, this is equal to tan hyperbolic gamma epsilon small ms by kt. Okay. And so ms divided by mu n is equal to a small ms. So you can say that this small ms is equal to tan hyperbolic gamma epsilon ms divided by kt. Okay. Divided by kt. And from here you can write this ms equal to tan hyperbolic Tc times ms by t. Actually here Tc has been written at the place of gamma epsilon by k. Actually this quantity gamma epsilon by k has a dimension of temperature, and this is actually the measure of critical temperature, which is also called Curie temperature. You will see now that at a temperature less than this Curie temperature, a ferromagnetic substance possesses spontaneous magnetization, and it behaves like a ferromagnetic substance. But above this Curie temperature, the spontaneous magnetization vanishes, and the material will behave as a paramagnetic substance. So this at this particular temperature, Curie temperature, this is the critical temperature at which the phase transition takes place from ferro to para. Okay. But how? We can say this. For this, we have to solve this equation 8. You can see that this equation cannot be solved analytically. There will be no analytical method for solution of such type of equation, because this is called a transcendental equation. Okay. And any transcendental equation finds its solution by two methods. First method is called graphical method, and the another is called numerical method. Here we will see the graphical method for the solution of this equation 8. And to solve this equation 8 graphically, we actually plot on the same graph, graph paper, two curves. this LHS, that is this MS, is plotted in against of MS. MS versus MS graph. MS versus MS. When you will plot MS versus MS, what type of curve you will get? That will be just a straight line passing through the origin, having the slope 1. That is, this angle will be 45 degree. In this figure, you can see this straight line, which I am marking by the name PQ. This is a straight line, and this straight line is a graphical plot of MS in against of MS. Okay. So I have written here that this curve, which is a function of MS, is equal to MS. And the another curve is drawn by plotting the RHS of this equation 8, that is tan hyperbolic Ts times small ms by t. This function is plotted again in against of ms at the same place. And the curve obtained after this plot has been shown by this curve, let us say Rs. This is represented by the curve Rs. Okay. Now you can see that these two curves intersect one another at 2 points. First point is here. Let us say this point is x, and another point of intersection is y. Okay. And there is also a third intersection, and this is at the origin. This is at the origin. Okay. So actually, from this graphical plot, we obtain the value of this ms, and these point of intersection actually gives the values of ms. But that depends on temperature, because in this function the temperature is contained here, and so the solution will depend on the value of Tc over T. What are the solution? You can see actually it is found from this graph that ms is equal to 0 when Tc over T is less than 1. It means the critical temperature or Curie temperature is less than the temperature T or the temperature of experiment, then ms is equal to 0. ms is equal to 0. Okay. And this actually represents this point of intersection at the origin. But when situation is just reverse, that is Tc by T is greater than 1, or you can say that critical temperature or Curie temperature is greater than this T, then actually there are three routes. For the point of intersection at x, the value of ms I have marked by m, and for the point of intersection at y, you can see the value of ms is minus m, and at this point, the point of intersection at o, the value is equal to 0. So there will be three values of ms in this case. First one is m, another is 0, and third one is minus m. Okay. But this second route, when you talk about Tc by T greater than 1, this second route, which is equal to ms equal to 0, is not acceptable. Why it is not acceptable? Because when you will take ms equal to 0, when the temperature is less than the critical temperature, okay, critical temperature, then from this expression for Helmholtz energy expression, we have seen when you will use the value m equal to 0 in this expression, you will get that this Helmholtz energy will be actually not minimum when m will be 0. When ms will be 0, then Helmholtz energy will be not minimum. Okay. but you will get that taking ms equal to 0, the Helmholtz free energy is maximum instead of minimum, and the system will be not in equilibrium. So for equilibrium of the system, definitely we should not take ms equal to 0, because it leads to the unstable state of the system. Okay. So finally, from this conclusion, you can say that when Tc by T is greater than 1 or Tc is greater than T, then there are only two acceptable values of ms, and those values are plus minus m. Okay. Now you can see that in this figure the intersection point M moves from this M to plus 1, this plus 1. Okay. And in this side this moves to minus 1. So actually this intersection point M moves to plus 1 as T tends to 0. Okay. And all the magnetic moments in this condition when T tends to 0 are lined up at 0 Kelvin temperature. It means all the magnetic moments are in the same direction. And as all the magnetic moments are in the same direction, so the resultant magnetization will be not 0, because magnetization means what? This is magnetic moment per unit volume. Okay, induced dipole moment per unit volume. So there will be a spontaneous magnetization. Okay, and you can say that there exists the possibility of ferromagnetism below a certain temperature, certain critical temperature, and that very critical temperature below which there is a probability of existence of ferromagnetism, that is called Curie's temperature. Okay, that is called Curie temperature. Again, you see that there are two roots plus minus m for T by Tc greater than 1. This degeneracy, there are two state it means. Actually, this degeneracy is why this degeneracy exists. Actually, cause of this degeneracy is that when you take H equal to 0, it means you are not applying any external magnetic field. Actually, in absence of any external magnetic field, there is no difference between the up and down spin. So actually, these are not two different states but same state, because up and down are the same thing. Okay. Now, generally, as I have told you, that for getting the value of m, we use the numerical method. For this, you have to make a program by computer, and then you can solve such type of equations, which is not possible in this lecture. And so I have written what will be the approximate values of this m obtaining by the numerical calculation, okay, using this Bragg-Williams approximation near T equal to 0 and T equal to Tc. Actually, the approximate value of m, which is computed numerically and near T equal to 0 and T equal to Tc are what? First one is m almost equal to 1 minus e to the power minus 2c by t, when Tc by t is much smaller than 1. Okay, and when this 0 is less than 1 minus t by tc, and this is much less than 1, in that condition it is seen that m is almost equal to a square root of 3 times 1 minus t by tc. Okay, these two results I have written here directly, so for writing in your examination you should remember it. Okay, now you can see that the value of m even when Tc by T is much smaller than 1, or it is 1 minus T by Tc is much smaller than 1. In both condition, m depends on the value of Tc by T. So you can plot a graph of m in against of T by Tc here on the basis of Bragg-Williams approximation, and you can see that the graphical plot of this m in against of T by Tc. Actually, you can see from this graph that when T by Tc is equal to 0, it means you are talking about 0 Kelvin temperature, then this m is equal to 1. You can see then m is equal to 1. Okay, and when T by Tc is equal to 1, it means temperature is equal to the critical temperature. Then you can see this m is equal to 0. Here T by Tc is 1 and m will be 0. Okay, m will be 0. So this is the graphical plot of m in against of T by Tc for the spontaneous magnetization in the Bragg-Williams approximation. Okay, so I think we have clearly understand the concept of Ising model utilized in Bragg-Williams approximation to deal with the problem of ferromagnetic phase transition. Okay, so thank you very much. In the next lecture, you will see the one-dimensional Ising model, which is also a very important concept for your examination point of view. Okay, thank you very much.